Okay, thanks for the introduction and thanks for giving me the opportunity of presenting this work. And so good morning, everybody, or good afternoon or good evening, depending on where you are. I will discuss some of the possible phases of matter, of cold and dense matter. And also the idea is to give you somehow, the environment in which this kind of research is being done, and what is, in part, at least, the current status of this research. So the outline of my talk is I will give you an introduction of matter and extreme conditions, and then on these, say, exotica, color superconductors and meson condensation. Just a few preliminary considerations. And so why study compact stars? So certainly one possible answer is that because they are there, so these are objects that we see in the heavens, and we want to know what they are. And also the other answer, in my opinion, is that this actually helps us understand the properties of hadronic matter. The reason will be clear pretty soon, and that's because somehow hadronic matter is simpler at energy scales. Certainly, there is the unavoidable problem that compact stars are far away, so it's not like in heavy ion collision when we have our experiment, we can smash heavy ions and see what comes out, or you can smash proton-proton or whatever particles you like, basically on in accelerators. And so and also in that case, say in heavy ion collisions, you have a plethora of things that you can look at. And actually, there is redundant information. Indeed, just part of the information is recorded and studied. In the case of neutron stars, it's pretty much the opposite. And so how to make progress is, of course, careful and stoical observations of the properties of neutron stars. And somehow, gravitational wave, the merging and the gravitational wave signal from merging is somehow similar not to heavy ion collision. Like the whole idea, the smashing stuff, you can look what is inside, possibly looking at what are the debris of the smashing. And but in order to make a real progress, you need some reasonable theoretical modeling of what's going on. Okay, because if it is you lack this part, then it's very hard to make progress. So matter and extreme conditions. So this is the QCD, so-called QCD phase diagram, and it is a grand canonical description on the possible phases of matter. Here there are three axes. There is the temperature axis, and on the horizontal axis you have the baryonic chemical potential, and there is the isospin chemical potential. So at low temperatures and chemical potentials, we know that we have hadrons, standard hadrons. But as the energy scale increases, then we have other possible phases of matter, which is at high temperature and relatively low chemical potential, the quantum plasma, which is studied in heavy ion collision, HIC in this figure. And instead, at large chemical potential, we have compact stars, which actually are also asymmetric in isospin. And so they occupy part of the diagram, which is somehow at large chemical potential and relatively large isospin chemical potential. And as you increase the baryonic chemical potential, quarks should deconfine, form so-called superconducting phase. And as you increase instead the isospin chemical potential above the pion mass, you should have a pion condensate phase. So basically, we will focus on color superconductors and pion condensate phase. Here are some reviews on if you're interested in color superconductors and pion condensation. So the idea is basically the following. If we start at low, so in this cartoon here, I present, say, the possible phases of matter as we increase the density. And so the first is just, the first column is just hydrogen, helium, iron, and whatever you have else, like at some point you have unbound neutrons, so the so-called neutron drift. And as you increase density, you're supposed to get to the soup of neutrons and protons. Finally, in the core, or possibly in the core, you have a quark drift, meaning that you have somehow unbound quarks. And finally, at extreme densities, and we shall figure out what are these extremes, you should have a soup of quarks. And then, as you can see, I've not only indicated the part of the star, but also the strong coupling, alpha S, which is running, meaning it is dependent on the, say, on the baryonic chemical potential. As we are in on the last column, sorry, there is the degrees of freedom. Okay, so if the interaction is confining quarks, certainly we only have nucleons and nuclei. Okay, but as we reach the confinement, the interaction is still strong. So the degrees of freedom should be quarks and gluons, and possibly Cooper pairs of quarks. And but still, it's strong coupling, so it's hard to make prediction. You cannot use perturbative QCD, which is something that actually you can do also in the extreme regime, which is not reachable in any compact star, where the strong coupling becomes weak. So what is the quark modeling? We have our knowledge is that hadrons are composite object of quarks and gluons. So we basically classify them in baryons and mesons. So baryons have 3 valence quark, and mesons have a quark and an anti-quark. And nowadays we also know that probably exist the tetraquarks or pentaquarks. So tetraquarks have been seen at HCB in this in these days. So, let's focus on baryons. These are objects which have a mass of about 1 GeV, and which is much larger than the mass of the up and down quark. Okay, so you should not think to protons and neutrons as bound state of quarks. Okay, that's the wrong picture. The radius of this object is of the order 1 Fermi. Okay, a similar thing happens for say pions, which have a mass of 130 MeV, much larger than the mass of the valence quarks, which is 3.5 MeV, and the radius of 0.7 Fermi. So in some theories, these are, baryons are seen as configurable bubble of energies like solitons, okay? And the pions are instead associated with the pseudo-Nambu-Goldstone model, but it's a technicality for us. It's just the fact that these are bubble of energies, and the bubble of energy gives the mass of this stuff, okay? And the reason, so the valence quark, as I was saying before, like up and down, here is the mass in MeV is just 3 or 5 MeV. And so most of the mass is in the interactions. An interaction is the color interaction, because quarks have 3 different colors, red, green, and blue. You're just 3 names for an internal degree of freedom. And there is associated SU3 color gauge group. Okay, so it's a non-abelian interaction. And the theory which describes this kind of interaction is quantum chromodynamics. We know the Lagrangian, and knowing the Lagrangian doesn't mean that you, unfortunately, doesn't mean that you have a solution, okay, that you can find a ground state of it's complicated by the fact that these gauge fields are non-abelian, that the interaction is extremely strong. How strong is this? So this is an old paper by Kaczmarek and Zantov, and as you can see here, basically there is a region at short distances where the interaction becomes small, so perturbative. But as you increase distance, you see in this chart, in this plot, there's not even one Fermi, which is typical size of baryons. The interaction becomes extremely strong. In any case, here it's already non-perturbative. Where it is perturbative? It is perturbative here at a distance, say, of about 0.1 Fermi. Okay, and that's because that's the inverse of the typical energy scale of QCD, which is about 300 MeV. Okay, and so the two main properties that at a large distance there is confinement, and at a short distance there is asymptotic freedom. So if you're able to squeeze matter in this region here, you can study QCD with its real degrees of freedom, that is quarks and gluons. If you're not able to do this, and so you're in this region here, it's your degrees of freedom are not quarks and gluons, okay? Because there's confinement, which is relevant. And so this is an important thing. So where are neutron stars here? Well, probably there are in a region at the core of neutron stars. These are probably in a region where there's a squeezing, so that we are well above saturation density, but the interaction is not weaker. Okay, it's a strongly interacting matter. So what to do? The thing that we can do is to look at the symmetries of QCD. These are it's somehow technical, but the symmetries are an important feature of a theory, because any macroscopic theory could preserve the symmetries of the microscopic theory. Okay. And in this case, we have a gauge group, which is SU3 color, as I said before. Then if there's massless quarks, there is a chiral symmetry. And there is a global baryonic number, which is preserved. So there are two possible paths. I mean, there are many possibilities, but these are the two main paths. The first is that you discretize, so you lose, instead of studying the theory in the continuum, you discretize space. And in this case, you have a lattice QCD simulations, which, however, have a sampling problem. You cannot use them at large densities because of the so-called sign problem. Or you can use effective field theories, which should preserve the global symmetries of QCD, but unfortunately they lack of the gauge field dynamics. So somehow you can have some qualitative and possibly some semi-quantitative result, but you should always be careful, okay, on what you're doing. So let's go back to the phases of matter, so to the QCD phase diagram, and let's give a look to which phases, and which theories we can study. So some methods. So perturbative QCD, as we said before, it's only valid at large energy scales, large temperature, or large isospin baryonic chemical potential, and you see that there's no overlap between perturbative QCD methods and compact stars. Okay. This is somehow well-established result, but there is overlap with, say, heavy ion collisions. The other method is the so-called chiral perturbation theory, which has overlap with the heavy ion collision and compact stars, and can be used. Say, I'm being kind of generous with it, but say, it can be a guiding method for studying nuclear interaction as well. Okay. And then there is a lattice QCD, as I said before, which has no overlap with the compact stars, but has overlap with hadron gas and, importantly, with the pion condensate phase. And finally, there are these NJL-like models, in which you have a contact interaction or I would include in this also Bhattacharyya-like models. Okay. So these are all models in which you completely lack the gauge interaction, and it is also you only have some kind of mediators, which can be scalar, a vector, or isotope. We have seen it in previous sessions discussion of this kind of model, but also models, very simple model with the contact interaction. Okay, and this you can use them basically everywhere. The point is that you lack the gauge dynamics. Okay, dynamics of the gauge fields, and this is an important limitation because, as an example we've seen before, the mass of nucleons is given by the gauge interaction. Okay. So let's now go to study what happens at large baryonic chemical potentials, so the so-called corresponding conducting phase. We have there's a possible classification of compact stars as a standard neutron stars, where possibly you have also hyperons in the interior. These are an object which have a radius around 10 kilometers, mass and range between 1 and 2 solar masses. And there are also the other possibilities that you have hybrid stars, where you have the confined quark matter in the core, and then you have a crust, an envelope, and atmosphere, exactly as in standard neutron stars. So these kind of stars can masquerade very well as neutron stars. They have a similar radius and similar mass. And then there are strange stars, which have also discussed part yesterday by Rangston Su. And these are a radius which can go, which can be very small, even a few hundred meters, and up to 10 and even more kilometers. And the mass, which is can be of the order also of 2 solar masses, but maybe in some models even larger than that. So they have there's no in principle you can change your parameters to have even larger masses. So there's some possibility to distinguish these strange stars from neutron stars from a careful measurement of radii. But the thing is that there are more options, because in the interior, actually, some color-space conducting phase can be realized as so-called color-favor locked phase, we will discuss very soon, or the 2 superconducting phase, or the crystalline color-space conducting phase, or combination of them. And unfortunately, there are several possibilities, and the transition densities are not strongly constrained. Somehow we know we should use QCD. The thing is that it's hard to make prediction using QCD or any other effective field theory. Okay. For example, let's look at this mass radius diagram. I'm reported here only a few nucleonic standard equation state. For some reason, I don't see the prompt, but anyway, so you name the MS1, slide 4, and BB2. These are standard, say, neutron stars obtained with different methods. And you can see SS1 and SS2, which I've just done using a Bagchi model. And Bagchi model, but I pushed them to have a large compactness. So it's hard to distinguish, say, SS1, suppose you have some measurement of mass between, say, 1.4 and 2 solar masses, right? And you want to distinguish them from BB2 or slide 4 or even MS1. It's very hard, unless you have a very precise measurement of the radius. But definitely, that's something which should be done. So if we have a precise measurement, it's okay. This has already been described by James and Cole's talks. And or you have a mass by observation. You have an object which has a mass, say, of around 0.5 solar masses and a radius of 6 kilometers, something like that, which is pretty hard to see. But in any case, it's hard. It's impossible to explain such an object as a standard nuclear matter. Or the other possibility is that you have an object with an extremely large compactness. I mean, compactness is m over r. So as an example, I mean, these two lines, S1 and S2, correspond to stars which also have a photon sphere. So they are extremely compact. But as you can imagine, a probably you already know, it's a difficult job. So you have to be very patient and to have a very precise measurement. What are the basic things we need to know for understanding color superconductor? The building blocks, first of all, which are quarks, which is quarks are point-like object. The baryon, as I said before, is of order 1 Fermi object, and diquarks, which can have a few dimension of a few Fermi. So they are in principle bigger than baryons. So what happens in matter? I mean, suppose you have a low density. I mean, low means much larger than what we can achieve on the Earth, but it's at such a density that you still have a gas or a liquid of nucleons. As we increase the density, there should be some kind of percolation. Quarks should be able to move from one nucleon to the other because there's some overlap between the nucleons. And finally, there should be a very high density. It's like a soup of quarks, in which, say, the typical distance between quarks can be of the order of 1 Fermi, or something less than that, but there's a correlation between quarks which are far away, and but they have opposite momenta. And this is exactly what happens in superfluids or in superconductors. There's a form of correlation between quarks. Okay, between fermions in general, and this is this means that basically your Fermi sphere, the only active fermions which are those close to the Fermi sphere are actually paired. Okay, so you have less degrees of freedom than in the naive Fermi picture. Why there's pairing? Well, suppose we can use a QCD. Okay, so if quarks are in the fundamental representation of color, so 3. 2 fermions are 2 quarks are 3 times 3, which gives an attractive channel, which is antisymmetric 3 bar, and there's a repulsive channel, which is 6. So this, what does this mean? This means that basically you can have exchange of a gluon between 2 fermions, and this is an attractive interaction. Okay. So suppose we assume that it works, we can assume that it works at any density. So at any density there is an attractive channel. Whenever you have a Fermi sphere, an attractive channel, the BCS theorem tells you that there will be pairing, so the formation of a superconductor, if you have a temperature less than the critical temperature. And the critical temperature for this object is very large, much larger than the typical temperature of cold compact stars. But the gauge interaction also gives you another thing. It gives you a confining bag for the Wallen sum of quarks. And this tells you that the system is self-bound. So it's very different from a neutron star, okay? And that's the reason why you can reach very small radii, okay? Because it is a self-bound object, it's like a drop of water. It has cohesive forces which keeps matter together, and you do not need gravity, okay, to make this thing stable. Instead, for a neutron star, if you turn off gravity, everything explodes, okay? The general expression of the condensate, no matter what is your the interaction that you are using, is of this form here. So here psi are fermionic fields describing quarks. I suppress the spinorial indices, and so you have a gap which is called delta I, which has where I runs from 1 to 3, and it is multiplied by 2 Levi-Civita symbols. One describes the antisymmetrical interaction, the other one is the flavor part. So it is completely antisymmetric if you have a spin 0, okay? And delta I, so is the gap parameter for quarks whose flavor and color is not I, okay? The condensate, notice, is a color charge, has a flavor charge and a baryonic charge, okay? So a diquark, of course, cannot be a color singlet. The corresponding symmetries can be broken or mixed, and that's the reason why you have a zoo of color superconducting phases. There are many possibilities here. Let's consider the 2 most studied possibilities, which is a 2-flavor color superconductor. So in the right panel, you have the 9 quarks, so UD and S quarks of 3 colors. Suppose that the strange quark mass is much larger than the up and down chemical potential. This means that you cannot populate strange quarks. So only delta 3 is larger than 0. So it's the pairing between the quarks whose flavor is not S. Okay. So here you have pairing between up and down quarks and up and down quarks. So the 3 S quarks are unpaired, and there remain 2 unpaired up and down quarks, which possibly can also make a different kind of condensate. But in the simplest QSC picture, they don't make a condensate. Okay. So what is the symmetry breaking pattern? And the symmetry breaking pattern is simply that you break SU3 color down to SU2. A breaking of a gauge symmetry by the Higgs-Anderson mechanism means that you have a 5-gauge boson that acquire mass. So that's the color superconductor. Superconductor, a standard superconductor is the one in which you break U1 electromagnetic, so you give a Meissner mass to the photon, and that's a screening mass. Okay, the same things happen here, but it is in SU3, which is broken down to SU2. Everything else remains pretty much the same. Okay, there's no breaking of global symmetries. This is a breaking pattern, which was studied long ago, soon after the discovery of asymptotic freedom. This kind of phase was proposed. Later on, was proposed a different kind of pairing by Mark, Alford, Jaikumar, Frank, in which actually you have pairing of all the 9 quarks, so maximal pairing of the quarks. In this case, you have a different breaking pattern in which the SU3 and SU3 color left and right are locked to a global group, and there is a residual zeta2, so also U1 baryonic is broken. So look at the breaking pattern now. So we have this mechanism at work, and so we have 8-gauge boson that acquire mass. So it's a maximizes color superconductor somehow. There's chiral symmetry breaking, so you have 8 pseudo number Goldstone boson. So if you turn on the quark masses, this Goldstone boson becomes pseudo, like the pions and the kaons in the standard model. And you also have a U1 breaking. Okay, so there is the system is a superfluid. And there is also this technicality. There's a rotation of electromagnetism, which becomes mixed with one of the generators of SU3 color. This is similar to the Weinberg angle in the standard model. So it's a kind of complicated stuff, but the important message is that there's the breaking of the locking of SU3 color with the global symmetries. Okay. Let's try to make a quantitative analysis. Suppose we want to know the correlation length. So we studied the gap equation, say the Dyson equation for the propagator of quarks. And we use QCD. Okay, so there's we have to resound some diagrams here. I'm not resounding vertices, a very simple scheme. So I have to solve this equation, which amounts to do this integral. Okay, so I have a delta on the left, which must be equal to the result of this loop integral, roughly speaking. This gives you a dependence of delta on exponential of -1/g. Okay, this comes from a collinear divergence in the propagator of gluon. Okay, there's only damping due to the Landau damping mechanism. And this was a known fact since 1979. That was PhD thesis, and also discussed by Son in 1999. Okay, so, but this is, as we know, is only valid at the extreme of densities. What happens if you use a contact interaction theory like Nambuyon and Asinio 1? Okay, you have contact interaction with the coupling constant G, and you want to do the same calculation, so the Dyson equation. What you find is that now you don't have gluon exchange, it's only a contact interaction, and the scaling is wrong. Okay, you get that the delta, so the inverse of the correlation length, scales as exponential -1/g squared. Before it was -1/g. Okay, so you have a wrong parametric dependence on the coupling. Still, I mean, you have the same mechanism. So quantitatively, you have pairing, you have formation of superconductor. if you use your parameters in the correct way, you can reproduce the CFL or the NJL or the QSC using NJL model. But you have to be careful that still you can make a semi-quantitative predictions. Okay, so delta NJ, so the inverse of the correlation length, should be taken in a certain range, and you should try to fix it somehow by observations. Okay, and this is what we will try to do in the following. And the way in which we can try to fix delta is looking at a different phase, which is similar to the one we discussed before, which are named the crystalline superconducting phase. What is it? I mean, if you have up and down and strange quarks of 3 different colors, and you typically you populate them with different Fermi momenta. Okay, if you increase the interaction, the Fermi surfaces have to match, because the BCS pairing and the BCS pairing fermions have equal and opposite momenta. So in QSC, you only have pairing of momenta for up and down quarks, which are, say, red and green, and in CFL, all of them have to match. These pictures tells you that actually your degrees of freedom are quasi-particles which have mixed color and flavor. Okay. Whenever there's BCS pairing, the Fermi surfaces have to match, must be equal. Now, in quark matter, in compact stars, it's not that easy to make Fermi surfaces equal. The basic reason is that there are weak interactions, and there is the strange quark mass has to be taken into account, which is around 100, 130 MeV, and there's electrical neutrality. So very briefly, if you impose the equations of weak interactions and electrical neutrality, you find a mismatch of the Fermi spheres. If this mismatch is larger than the so-called Chandrasekhar-Clugston limit, then BCS pairing cannot occur. Okay, so a different kind of pairing. And this is well known in condensed matter physics, that it is possible to have a non-isotropic pairing, which is named the FF law or LOFF phase, in which there's a pairing only in restricted region, which are these red ribbons here, on the top of the Fermi spheres. On the right panel, you have a plot indicating the pairing regions, so the regions where pairing occurs, and you can see that is so here T momenta are in MeV, and so pairing can only happen. It's not happening on the whole Fermi sphere, but only in restricted regions. This tells you that probably delta is smaller than in QSC or CFL, but somehow this is kind of more realistic in the sense that it takes into account the possible effect of neutrality and beta equilibrium inside compact stars. Of course, instead of just 2 ribbons, you can have multiple regions, but you cannot have overlap between these regions because superconductivity is a coherent effect. So you cannot have simultaneous pairing of quarks on the top of the Fermi spheres. And this led Krishna and Rishi to Jaikumar and Sharma to propose some kind of arrangement of this ribbon in crystalline phases. And this is basically the phase diagram that you have, with the important caveat, okay, that this is obtained by NJL plus Ginzburg-Landau expansion, okay. So once again, probably it's quite possible that in this range of ms square over mu, there is some crystalline phases. Which phase is favored depends on the model that you're using. If you're using QCD, we don't know which phase it is, but possibly it will be a crystalline phase, okay? So this is just a comparison between results of the free energy obtained using NGL plus Ginzburg-Landau expansion. Okay. So an important aspect is that there are 2 important aspects. The first one is that quasi-particles have a linear dispersion law, here written E equals C, which is a kind of Fermi velocity, times C, which is a residual momentum. So it's a linear dispersion mode. So we have gapless modes, okay, on the top of the Fermi sphere. And this is a result of incomplete pairing at the Fermi sphere, okay? And the velocity of the Fermi velocity, of course, takes into account the kind of structure that you have. Here I reported two plots of for the BCC and FCC crystalline phases. So the speed of sound goes from 0 to 1, depending on the angle, on the polar angles, theta and phi, okay? So if you have a crystalline phase, certainly it can be rigid, okay? There's a standard way of studying things. You perturb your crystal and you study low energy fluctuations. And basically the rigidity is associated with the spatial modulation of the gap parameter, because this is this modulation which is rigid. And what we found is that actually the shear modulus can be 20 to 1,000 times larger than the standard crust of neutron stars. Okay, so it's an extremely rigid object. And then what? Then let's try to compare with astrophysical observables. As an example, suppose you have a star which is deformed, so it has so-called mountains, even if they are only a few centimeters high, on the top of neutron stars, which are non-axis symmetric. Okay, so a configuration like this. I mean, I've been deforming a lot the neutron star. So it is a non-axial symmetric deformation. Then there is some resistivity, and so if it's rotating, it has some. It is emitting gravitational waves. Okay, and that depends, of course, on how much deformation you have. But since the crystalline phase is extremely rigid, it keeps on staying large ellipses, much larger than the standard neutron stars. The deformation can arise in the crust and the core. That depends on your model, and deformation also depends on the breaking strain. Okay, the breaking strain is the maximum. Somehow, it's the maximum strain that for which you have an elastic response. Okay, if you have in standard material, at a certain point, if you stress too much, your material will break. Okay, and it's very hard to have a prediction of the breaking strain, but it's certainly something which should be done. And the reason is that to have large gravitational wave amplitude, you need a large shear modulus and a large breaking strain. And these are some results from past years on the comparison of LIGO data. And there's a paper of 2007 and two papers of 2007, one by Lane and the other by the group of Niels Anderson, which took our results seriously. Let's look at the Lane on the left, on the top left. Basically, you see there's delta and mu, okay? And that rectangle is somehow the allowed region of NJL model, or what you should expect. I mean, delta running between 5 and 25 MeV, and chemical potential around 400 MeV. This is a Quark chemical potential, okay? And so if the breaking strain is of the order of 10, so these are exclusion plot. Everything on the top of this curve is excluded. So if the breaking strain of the order of 10 to the minus 3, there's only the upper part of this rectangle which is allowed. And this was done with, so you are actually reducing the phase space, okay, for your model. The idea would be to rule out this model somehow. But I've redone this in the review in 2014 using updated LIGO data, and once again you find similar results. Unfortunately, these results depend on the breaking strain of the crystalline cross-conducting phase, which is not known, and whether there's some agent which can deform, maximally deform the star, which is because the idea is that actually there's a way of deforming it. So this is the maximum deformation that it can have, but you also should have an idea if there's something which can deform your star. It's not that easy, okay, to find some energy. The other possibility, which was in part mentioned also yesterday, is that it's about cooling. So this, since this is in the crystalline phase, so let me say, in the CFL phase, or in any superconducting phase, typically there is a Gibbs factor, e to the minus delta over t, which is a reduction of emissivity. Okay. But in the crystalline phase, there are gapless modes. In this case, you have a cooling which is very similar to Ampere Quark matter, meaning that happens because direct nuclear processes are allowed. And so there is a big difference between nuclear and quark matter description. And of course, as you have seen yesterday, the cooling starts from the interior. Okay, and indeed, in this simple model, where we were considering just incompressible matter with a core of quark matter which is of 5 kilometers. The cooling is much faster than in standard neutron stars. Okay, so this would be an interesting effect. In this case, the diagonal star cannot masquerade as a standard neutron star. So precise cooling measurement can help us to disentangle, distinguish this model. Of course, this has been done for standard for incompressible matter, which is unphysical, but one can extend it to standard star. But then, if you do that, you have you're assuming some model. Instead, this is just assuming that you have a core of crystalline corresponding phase and, say, an envelope which is of standard nuclear matter. Then let's look at another possibility, where the possibility to have a meson condensation compact stars. This is an old topic discussed first by Migdal in the 70s. And so the idea is the following. Suppose you have a form of Bose-Einstein condensate, which is a coherent state of matter in which a large number of particles occupy the same quantum state. You pretty know what it is. So if you have bosons and you are temperature above critical temperature, they occupy all the possible energy levels. But as you decrease the temperature and are below TC, basically they want to occupy the ground state. There's statistical attraction between bosons. What are the basic requirements for this to work? It's a mass particle must be bosons or boson-like. So Cooper pairs pretty much work as effectively as the bosons. The system must be cold, this means below the critical temperature, and the particles must be stable, which is something which sometimes is forgotten. And so in ultra-cold atoms experiments, here as the velocity distribution, you find that when the temperature is below TC, there's a clear kind of condensation of velocities, and this is done for rubidium-87, which is a bosonic. It's a bosonic atom. It can be cooled efficiently, so temperature of the order hundreds of nanokelvin. It has a lifetime of 10 to the 10 years. So the experiments last 10 to 3 seconds. There's plenty of time for doing the observation. What about pions? I mean, they are bosons, okay. They can be produced at low temperature in compact stars. They have a small problem that they decay in 10 to the minus 8 seconds by weak decay. Pions decay typically in muons, and because of anyway, they decay in leptons. So that's an important issue for us, okay. So it seems hard to degenerate pions because they quickly decay. But the same thing should be, I mean, happens for neutrons. They decay in vacuum in about 800 seconds. But in medium, neutrons can be statistically stabilized. So it is possible that Pauli blocking plus charge neutrality allow us to have a large number of neutrons inside the compact stars. So this is already seen in the crust of neutron stars. So if you increase the density, so the right column here is the transition density, this is taken by paper by Anderson and Pichon, but there's several calculations and several charts that in the past. You see that zeta over A, so the number of protons over the number of baryons, decreases as you increase the density. Okay, so this tells you that effectively the number of neutrons is increasing. At a certain point, you reach a neutron rip. By the way, notice that the double horizontal line signals the way in which we can reach. It's the last isotope which is produced in experiment. Okay, everything else here is theoretical working plus extrapolation plus other informations. Okay, so we cannot reach very high densities. We cannot reach a neutron rip, but kind of close to it. And when there are many unbound neutrons, we know that zeta over A is of order of 0.1. So this number, zeta over A, continuously decreases, okay? But the other thing is that also there are many electrons in our system. The chemical potential of electron monotonically increases as we increase the density, okay? So this is an important thing, because we know that pions decay in muons and muons decay in electrons. So it's possible to close the phase space for decay of pions. Indeed, the pion decay is Pauli the pion decay is Pauli blocked if the chemical potential of electrons is larger than n pi. Very schematically, I mean, in standard matter in vacuum, n pi is larger than me, so n pi decays in electrons. But if you increase mu e to reach n pi, then there is statistical equilibrium. Okay, a similar effect can also stabilize chaos if the effective mass of chaos is below the kinematical threshold for the decay. There's a number of caveats. Let me skip on this. This is a very, naive picture which I've been presenting. But we can do some general considerations on meson condensation. First is that the energy spectrum of pions becomes split if there is isospin chemical potential. That's very similar to Stark-like effect for electrons. Okay, so there's the splitting proportional to mu I of charged electrons, which are the electrons which have an isospin charge. So the effective mass, say, of pi plus is n pi minus mu I. So what happens when mu I is larger than n pi? For mu I equal n pi, the effective mass of pions becomes 0. But what happens for mu I larger than n pi? This effective mass is vanishing. That means that we are expanding around the wrong vacuum. So if mu I is less than n pi, the stable vacuum is the one in which pi plus has no expectation value. But if mu I is larger than n pi, the curvature at the origin is negative, so it's the wrong sign. Somewhere else there should be a stable vacuum. Okay, this is general, and this also happens for charged chaos and also for neutral chaos, because they have strangeness and isospin charge. So mass splitting can lead to the onset of an instability. And this, just looking at the splitting of the masses, you get this red hexagon here, okay, where you have second order phase transitions between the normal phase, which is in the center, and the pion condensed phase or the kaon condensed phase as you increase mu I or as you increase mu S. Okay, this is a result which was obtained by Kogut and Turner several years ago, and using chiral perturbation theory. But it's simply a result of the mass splitting that we've seen before. Chiral perturbation theory is a method for us to have, so far we had a qualitative analysis. Now we want to have a quantitative or semi-quantitative analysis. So in effective theory, working at scales less than 1 GeV is the breaking scale of chiral perturbation theory. And the recipe is very simple. You have expand around a non-perturbative vacuum. using the symmetries of QCD, the global symmetries of QCD. And since you're expanding around the non-perturbed vacuum, you have control parameters. In the simplified picture that I'm presenting now, we do not include baryons and vector mesons, which just means that the baryonic chemical potential should be less than 1 GeV and isospin less than the rho mass. So I can write the leading order Lagrange, where in sigma I have my bosonic degrees of freedom, meaning for SU2 it's just the pions. And for SU2, so I have these very simple ansatz. These are radial field and some angular field. These are sigma Pauli matrices. I put in the Lagrange, in the static Lagrange, so I still know dynamics, and I maximize the Lagrange. What you can easily find is just very quick calculation, is that if mu I is less than n pi, cos alpha is equal 1. So there is this is a standard vacuum. But if mu I is larger than n pi, there is a symmetry breaking. Okay, there is instead of O3, you have a residual O2 symmetry. And this is so a breaking pattern is associated with a symmetry, a change of symmetry of your system. Then, since as we have seen in the beginning, there is overlap between tidal perturbation theory and lattice QCD simulations at low baryonic density, you can compare and tune your result with the lattice QCD. And we have done it in this paper. And also, I put here on the right the perturbative QCD result, and which, however, are is an extrapolation of perturbative QCD result. Notice that so this is the dots with the error bars are obtained with lattices with the different number of points, so 16, 20, 24. And instead, the dashed line is the chiral perturbation theory. We pretty much catches the maximum of this curve. And actually, we have a prediction. We had the prediction for this, which was mu I over m pi 1.276 is an analytical result, which is extremely well reproduced by lattice QCD simulations. For different sizes, you have 1.2, 1.25, 1.275 m pi. Okay, so it's extremely good agreement. So this tells you that your effective model is working pretty well, at least in this regime. And so, what to do with this? We propose the existence of so-called pion stars. Okay, pions are stable, so the effective mass of, say, pi plus is 0, so it cannot decay in anything. Okay, and this means that it is possible to form a star completely made of pions. And the German group took this seriously, and actually they produced the plots of the m over r. And depending on the composition, whether there's pions or in the electrons, pion muons, or only pions, they found a different m over r, m versus r behaviors. Okay. But this is just say the beginning of the story, because of course one should look at other possible servers like oscillations or cooling of these kind of stars. So just as a summary, for particle physicists like me, compact stars are excellent squeezers. So they can help us to reach extremely high density, so a regime in which we can study QCD where the correctness of freedom are quarks and gluons, possibly at least. Then this gives us a plethora of exotic phase, and which should be studied with effective model. And we have to become patient, I mean, before ruling in or out of model, because we are accumulating observations, and possibly with the precise measurement of compactness or of radii, it should be possible to rule in or out at least some of this model. Okay, thanks for your attention.
Thank you, Professor Massimo Mannarelli, for this wonderful talk. We have few questions in the chat box. I will take the first question is from Pratyusha Baral, why don't we have proton stars like neutron stars?
Why don't we have proton stars?
Yeah.
Oh, well, the thing is that you have to somehow to neutralize protons, right? So the thing is that there's a proton capture process which minimizes the energy, and so you have populating neutrons. It's basically Fermi statistics, okay? It's much easier, so you reduce the free energy of the system are simply populating neutrons by electron capture of protons.
Yeah. The second question is from Bharat Kumar. How to calculate transition density? I mean, which model have you used?
Transition densities. It's not easy, an easy task and not easy question. The thing is, in order to certainly, I mean, you need a good modeling on both sides. Okay, so you need a good modeling of nuclear matter and a good modeling of quark matter. Okay, but as we know, we lack both of them. So the best thing that you can use is to use a model that works on both sides, which is, as we've seen before, an NJL model. Okay, so use NJL-like models to compare this density. You fix the parameters to NJL model to some known properties of matter, and then you determine the transition densities. Of course, as I said, mu quark of order of 400 MeV is just of order 400 MeV. Okay, can be smaller or larger by some factor. But we kind of believe that that's the right. I mean, the good thing is it's in the right ballpark, meaning that it's a almost the point at which nucleons start to overlap. Okay, just geometrically. So that tells you that actually it should be around that number.
Yeah. So next question is from Prashanth Jaikumar. Is it possible to have something like defects in the crystalline superconductor similar to normal crystals? It might lower the shear modulus and thereby improve agreement with LIGO data in the exclusion plots you showed.
Maybe. no. Maybe. I would say it's hard to have defects. It's unfortunate. We thought about that, but it's hard to have a defect. Somehow, it can happen if there are bubbles of confined matter. Okay. Somehow, that's the only thing that came to our mind. But if you have bubbles of confined matter, then of course, say in pasta-like phases or something like that, you certainly can lower the shear modulus. So I agree with the Prashanth point, but it's really hard to make this kind of calculation.
The next question is forwarded from YouTube Live, Avidesi. Are the hadronic matters classified into any group?
I don't understand much this question. I mean, the classification that we have of hadronic matter is based on roughly on symmetries. Okay, so say baryon as baryonic number 1, meson as baryonic number 0. Now there are these tetraquark and possibly pentaquark states, which are, so we also classify them by parity and other quantum numbers. So there is certainly a classification of hadronic matter. Regarding the confined phase, we classify them by the residual symmetries with respect to the vacuum. Okay.
The next question is from Sayantan. Are color superconducting phases affected in presence of magnetic fields?
Yes, but not that much. And so the it's much more important for a coarse-conducting phase, the rotation. Okay, magnetic fields basically propagate inside this kind of matter because most of the phases, the U1 is only rotated. Okay, it's not screened. That means that it can penetrate in matter, in coarse-conducting matter. But rotation can produce superfluid vortices. And indeed, the thing is that we made actually a calculation on the possible glitches which can originate in the crystalline phase, where you have pinning of superfluid vortices to the crystalline structure. And the mechanism that you have for producing glitch is more complicated because you have two crusts. So you have the standard neutron star crust, but you also have the crystalline phase inside. So it's and also you can have other phenomena like Ruderman-like earthquakes, core quakes, and similar. So it's there's a lot of dynamics which can be associated with the crystalline phase, but the magnetic field, in our opinion, is there's been calculations of the effect of magnetic fields, which can be pretty large in neutron stars, but the energy scale is much larger than the baryonic or the quark chemical potential.
Okay, thank you. So I would like to ask one last question from my side. Can you go to slide number 14? 14.
Yes.
Yeah, it's maybe a silly question. I'd like to know, you can see the MR curve in two different cases. For the nuclear matter US, the slope, and for this, why these two kind of USs, the slope is different.
Sorry, say it again. For strange stars and nuclear matter. Yeah. Well, the reason is that strange stars are self-bound. Okay. So self-bound matter can exist with any small mass and radius. Actually, there's a limit here. We started from 2 kilometers. But anyway, it's like a drop of water. Okay, if you put more water, it becomes larger. So it's just this effect. Instead, for neutron stars, you have the opposite behavior. Okay, as you decrease the mass, the radius must increase. And you have a similar effect only to those that you have in standard neutron stars, only when you reach a point where gravity is so strong that makes this curve bend. Okay, so in this part here, before you reach the top mass, gravity is extremely compressing matter. So it's instead of being self-bound, it is still self-bound, but gravity is pushing more stuff together. So and as you know, I mean, if you go to large radii, neutron stars probably explode. Instead, at small radii, these kind of stars make strange stars make so-called strange lights. Okay, which are small bumps of material of strange matter, and there are some caveats here, okay, but the basic picture is this one. So these are any self-bound object piece, like you can also make a self-bound object using a polytrope, okay, and you have a plot similar to this one.
Yeah, thank you. One more question came actually in chat box from Devaruti Chatterjee. Which quark phases can be expected to be appear in the post-merger scenario?
Hi, Devaruti. Yes. The thing is, the equation of state, as we know, is different there because the temperature is higher. Okay. Now the point is whether the temperature is of the order of delta or not. If delta is, suppose the temperature in the core is extremely large, say larger than tens of MeV, then the effect of any superconducting phase will be very, very small. But if it resists enough time to cool, and or if it doesn't reach such a large temperature, And then I would expect some kind of cross-conducting phase. And if I were trying to study this kind of thing, I would certainly start with the CFL, okay, to see whether it's energetically favored. And otherwise, because it's homogeneous and it's simpler to study. And then try to figure out whether the crystalline phase is present. I would not, maybe yes, it's also useful to study QSC, but I would say that the QSC is less favorable in these circumstances.
Okay, thanks to one.